Hi, and welcome to another episode of Haltech's Technically Speaking. Today, we're here with Herman from PRP. We're talking about all things Nissan crank angle sensor. Now, before we get into custom trigger kits and all this sort of stuff, we first need to understand what the trigger system on the engine actually does. So, if you've got an EFI or an electronically fuel injected engine, the thing will have a crank and or cam sensor only. Now, this is where the confusion comes in. These two sensors have two sort of primary roles. So we'll talk about our crank sensor or our trigger sensor first. Now, this sensor can be found on either the crankshaft or the camshaft. This thing's primary job is to tell us, it's a reference point for each cylinder of the engine, and it also tells us how fast the engine is spinning. There's also a second sensor, which we normally call the home or synchronization or the cam sensor. The cam sensor's primary role is to let the engine management system know exactly what stroke and cycle each piston is at. So now we've got our two sensors, our crankshaft position sensor and our camshaft position sensor. Both of these sensors can be found in one unit, and a really good example of this is the Nissan crank angle sensor. So it's one unit, it's mounted on the front of the exhaust camshaft, and it's actually got two sensors or two signals coming out of the cam angle sensor. So one of them tells us which piston is coming up to top dead center compression next. The other sensor is giving us our speed sensor. So that's giving us our engine RPM. All makes sense so far. There's all different trigger types, so different engine manufacturers have different triggering signals, whether they be digital or reluctor. They've got different number of pulses, where a Nissan crank angle sensor, for example, has got 360 pulses for the RPM counter or the trigger, and then it's got 4 or 6 pulses depending on if it's a 4-cylinder or a 6-cylinder, for example. So it'll have, if it's a RB, like the example we're going to use, it'll have 6 windows for our home or synchronization or reset signal. So knowing this, we now know that the engine management system needs a position sensor and it needs a speed sensor. The problem that we've got when we come to our Nissan RB engine is that, well, there isn't really a problem up until a certain power level. The crank angle sensor spins, it sends the signal to the engine management system, and the ECU can then fire the injectors and fire the ignition accordingly. Where we do start to have a problem is when we start to modify the RB engine. So what happens is we start fitting bigger valve springs, bigger camshafts, we start to do higher compression, and all of a sudden the timing belt, or the belt that sits across the cam gears and across the crank gear, starts to have a bit of lash in it. So as the camshaft starts going back and forward, as you're starting to rev this thing, all of a sudden the belt gets slack in it, and all of a sudden the gear and the camshaft has slap in it, and then before you know it, the angle sensor that's mounted to this gear also starts to get slap in it. This results in the engine RPM in the ECU starting to get jitter, but more importantly, we start to have problems with timing accuracy. Now keep in mind here that it doesn't matter what brand of engine management system you have. If we've got a bad crank and cam angle sensor signal coming in, the ECU is always going to have bad ignition timing accuracy going out because the signal coming in isn't consistent. So there was absolutely no chance that the engine management system has a hope of firing that ignition timing at exactly the same point every time, because the signal coming in, it's not reliable. So to talk more about this and understand how to fix this problem and why this problem exists, Herman, first of all, thanks for coming and chatting with us.
Very welcome.
We've got a whole bunch of PRP stuff in front of us here. We've got a whole bunch of gears. Can you explain a little bit about what this is and how it's going to fix it?
Sure. So look, you touched upon the crank and cam being on the cam previously with the Nissan RB. We're speaking about an RB, but it's applicable to all 4-stroke engines. First of all, I just want to mention that because the crank is half the gear itself is half the speed, is half the size of the cam. It spins at half the engine speed, being a 4-stroke, suck, squeeze, bang, blow. We are only getting one signal here every 2 crankshaft rotations. So, in
Can I
saying
stop
that,
you? That's probably a really good point that you bring up there. So the hint to this that we always see so much confusion with in a 4-stroke engine, being that the hint for me is always that the cam gear has twice the number of teeth
absolutely.
as the crank gear.
Yeah.
Camshaft spins 1 time, crankshaft spins 2 times, suck, squeeze, bang, blow. 4-stroke engine. So this is exactly the reason why we can't get all the information we need to determine where cylinder 1 top dead center compression is just off the crankshaft. We would need to have 2 sensors in order to do that.
Now to do that properly, we split the crank and the cam. We call cam home. So you have on the crank, this example is 12 teeth. On the cam, we have 1 tooth. So what happens is, we call this a mechanical 12 and 1, but the ECU actually sees 24 and 1 because it's spinning at half engine speed on the cam. So I just wanted to make sure that everyone was aware the difference between a 12 and 1, a 12 minus 1, which would be 12 teeth knocking a tooth off here to give your ECU a partial home reference on the RPM on the crank. Is that right?
That's right. So what that means is that when we talk about 12 minus 1, there would be 12 teeth, but minus 1. So 12 with 1 missing. That means that when this thing spins around, if it's got 12 teeth in total, there's no unique point. So every time that the engine management system looks at that, it has absolutely no idea which cylinder is coming up to top dead center. All it knows is the engine speed. By knocking 1 tooth off and making it 12 minus 1, there's now a unique reference point on the crankshaft. So being a 4-stroke engine, every time the crankshaft spins around 1 time, I know that cylinders, let's talk about the RB,
Yep.
Cylinders 1 and 6, they're called the opposing cylinders because they do this at the same time, except one of them will be on the compression stroke, one of them would have been on the exhaust stroke. So if there's 1 tooth missing off here, even though I don't have all of the information to fire each injector individually and each coil individually, with 1 tooth missing here, we can still fire the engine and run it, but we will do wasted sparks. So we'd fire 2 coils at a time and we'd fire 2 injectors at a time. Doing this with the 12 minus 1 system helps to get engines started up and running faster because the thing will fire the ignition and the injectors on 1 crank revolution instead of possibly up
2.
to, what, 2 crank revolutions? Oh yeah, 1
Before
cam
we see a
revolution.
home anyway. So.
Spot on, for sure.
So in saying that, there are ECUs that won't cop a 12 minus 1. We're not going to call it an 11 tooth because it is 12 teeth missing 1. So you check with your tuner on that. When we go to when we go to the software, you might pick a 24 and 1 because obviously this is spinning half the engine rotation, as we mentioned before. Now, I just wanted to go and mention, we've covered 12 minus 1, we've covered 12 and 1. We now just wanted to go and mention why, we get asked a lot, why should I cut that tooth off? It's up to the tuner. We're not going to get there. We're not going to go into that. It's up to the person that's actually doing the job. There's an option for it. Ultimately, you can have more teeth. And we get asked all the time, why don't you have more teeth? We use a magnetic Hall effect proximity sensor. It likes seeing a low tooth count. 3 teeth, 6, 12 teeth, works really well. If you go to a reluctor type sensor, it likes seeing more teeth, like the JZ might have. Do you want to talk a little bit more about reluctor versus proximity?
Well, there's also a lot of magic in this, where this is probably, there's a lot of confusion in Hall effect and reluctor style sensors. So a reluctor style sensor typically has a higher tooth count. It's a 2-wire sensor that outputs an AC signal. So it's probably a bit in depth for what we're talking about here, but basically an AC sensor, something like that, is more suitable for a high tooth count. A Hall effect style sensor like this does actually have inbuilt circuitry to filter out extra teeth at a certain frequency. So we need to be very cautious to make sure that we use the right sensor with the right tooth count. Without doing that, we can run into all sorts of problems. So when you're picking a crank sensor and a cam sensor, it's really important to get the right sensor that's compatible with the number of teeth that you're trying to use. Because without knowing, you could be picking a sensor that's got some internal filtering then you're in for a world of pain when you start to get to a particular tooth frequency and the sensor starts filtering out those teeth, and before you know it, you've got all sorts of trigger problems.
You're absolutely right, Scott. Now I want to talk about how we split up this crank and home signal and how we set up this new trigger type. So basically, we've already spoken about the standard crank angle sensor. You've got 360 degrees on crank rotation, and you've got your 1 in 6 home. So we simplify that, and now we have a single home on the cam. It's picking up once every camshaft rotation, and that's taking care of all our home needs. Now we're eliminating our belt slack issue, our slop issue, and all the other inherent issues we have with an all-in-one crank and cam, and we're putting the RPM signal down the bottom.
Before you go on with that, I just want to point out here that the single tooth on the camshaft, we're not doing any ignition timing calculations based on that one tooth per se. This one tooth, if you think about this like a reset signal, so what's happening is the engine spins around, we see all the teeth on the crank, we do all of the work of the engine, so we fire off cylinder 1, 5, 3, 6, 2, 4, then the ECU does nothing. It just sits and waits for this reset signal to occur. Once this reset signal occurs on the camshaft, it then knows to go back and start doing the work off the crankshaft again, where it starts doing the real work of firing the ignition timing accurately off this crank sensor.
Might also add there's speculation that once the ECU sinks, it no longer needs a home. Can you debunk that for me?
This is partly true. If you've got a missing tooth off the crankshaft, there is some truth to this.
But saying we don't, let's say we're running a standard PRP12 cog.
If you drop the cam sensor, so Haltech does not do this. I can't speak about all brands of engine management, but Haltech doesn't do it. And the reason why we don't is because of those 12 teeth, so 720 degrees divided by 12 teeth under 2 revolutions, so that would be 30 degrees. So each of these 2 teeth is 30 degrees of ignition timing. So if we added or removed an extra tooth, so let's say you had a noisy event come through, or you have a sensor problem or an air gap problem, or you could have a range of problems, all of a sudden the engine is running advanced or retarded by 1 tooth.
It could be 30 degrees.
For however long.
That's a blown engine.
Straight away. So while this is not a common thing to happen, but there's absolutely no need to drop the cam sensor because you can resynchronize every single cam event. Like engine management systems, microprocessors operate so fast that an engine running at 10,000 RPM, it's slow and boring for a microprocessor. Everyone talks about MIPS or millions of instructions per second and all of this stuff. It's so far away from the limits of a microprocessor that we don't even talk about that stuff. Like the thing is barely jogging it in at these sort of speeds.
Barely getting out of bed.
With these tooth counts, it's not even a thing.
All right, so we are keeping the home signal intact. It can re-reference and realign itself as often as it needs to, but it's got to be there. You don't just disconnect it or ignore it at a certain RPM or whatever.
We don't do it because there's no need to be doing that.
Excellent.
So now that we've got these parts in front of us, Herman, can you show us how would you fit one of these on the RB series engine?
Start with a cam. It's quite simple. There's a cam plate with a magnet. Here's a similar one, goes up the top. And then we offer a billet crank angle sensor bracket. You can use the original. Basically, it's a small Hall effect sensor that reads that signal. Now it's set up, we recommend 0.8 of a mil off the sensor. Now this pitch on this M12 thread is 0.8. So you wind it all the way in until it hits the magnet on the sensor, and then you back it off 1 turn and it's gapped beautifully. So it only takes, even without a feeler gauge, it only takes minutes to fit. That's the home sorted.
So we're talking about the air gap on that sensor between the target material and the actual sensor itself. Awesome tip about thread pitch, which is something that it's so easy to overlook. If you've got a 1 mil thread, you turn it in, it's 1 mil. If you've got a 0.8 mil thread, 1 turn moves 0.8. So gapping that sensor should be super easy.
You're welcome. Now, once you remove your old gear, you fit your new gear, obviously, you've got to gap your sensor over the middle of that gear, over the middle of that tooth, as close as you can as possible. Now, when you've got a harmonic balancer like an OEM that comes in really close to that gear, you don't have much of a gap. Our bracket leaves a couple of mil before you hit a balancer. So any aftermarket balancer or OEM works with this kit, but there's a couple of washers to space that out. And if you don't quite have it, because all cranks are in different spots, we found oil pumps, some people run gaskets, some don't. There's long and short noses. Lengths of cranks differ. So you go and set it up and make sure not only your air gap is right, but your alignment from your sensor over your tooth is in the middle. Then you go and set up your air gap. On the crank, we recommend 1 mil, which would be all the way in, and 1 screw out, one turn out being a 1 mil thread pitch on that sensor.
Okay, so once we've got the cam sensor and the crank sensor attached, how do we synchronize these, or what are we going to do with that in order to make sure that that cam tooth occurs at the right position?
Well, I'm going to explain how you should start off with setting that up, and I'll let you take over the software component. But you don't want a cam signal to land on a crank tooth signal. So you want it to land between the gap there. So say this is firing an RPM signal dead on. Your cam needs to be somewhere between both those teeth. So I like to set it up at, say, 20% off that crank is where your cam signal will start firing. Then you can allow your belt stretch to have that much movement before, which is 30 degrees before it hits the next tooth. Is that right? So what happens when why don't we explain what happens when you're poling out, when you're hitting a home signal over a crank signal.
And this is actually coming back to the very beginning of the whole, this is the problem.
Yep.
Starting from the very beginning. So
belt stretch.
This thing has got 12 teeth, it's 360 degrees. 360 degrees divided by the 12 teeth is 30 degrees. So within that 30 degree window that we've got, we want our cam position sensor to occur somewhere in that range. But as this engine accelerates and decelerates and the belt stretches, we can see up to 8 degrees. So that's just, again, that's 8 degrees of cam belt deflection, which is insane. And
that's massive.
That's the whole problem that we've got with the crank angle sensor and ignition timing and all that stuff in the very beginning. That's why we're crank triggering this thing. So how do we stop that cam tooth from moving across a crank tooth when the belt's moving by that much?
Yeah, good question. And we know the belt's growing that much. We know we've got that much deflection, so we allow for it. Now that we've got a home signal, we know where it's firing, we know where the crank is, so I like to set them up at 20 degrees gain. That way you've got plenty of room to move before you start poling out on the next tooth, and you've also got a bit of movement coming back. Now, when you have belt deflection issues and you have that 8 degree problem, it's always going to retard the timing, which is not going to hurt your engine. But if you're pushing your engine to the nth degree and you're tuning it to try and you're almost detonating it to get the most power possible, you're going to pull it back a little bit to be safe. You're going to have a situation where that engine is tuned to its max, allowing for belt deflection. You go and throw a new belt on it for whatever reason, it's only moving 4 degrees. What happens then? You've got too much timing.
And this is a big deal, because something as simple as you take it to your performance shop, all done. If you put another timing belt on this thing and your tensioner is greater or less, more or less belt deflection really does have an impact on the actual ignition timing of the engine.
It's too sloppy.
So Herman, we've talked about this kit with like huge horsepower applications, but with this much belt deflection, I'm sure even smaller street cars are going to suffer similar sort of things. Have you got any applications that you've done or any real world sort of testing there?
Absolutely. And look, just to give you an idea how much it makes, how much of a difference it makes on a high horsepower application, just to touch on it quickly, it could be 4 degrees, could be 100 kilowatts, it could be 150 kilowatts. It's massive. On the small scale stuff, 200 kilowatts, 300 kilowatts, 3 or 4 degrees ignition timing, if you're tuning it for performance, it could mean 30 kilowatts. Now, 30 kilowatts on a 300 kilowatts, 10% gain, that's massive. You'd take that, wouldn't you?
Yeah.
So absolutely imperative as far as I'm concerned.
Mate, I really appreciate the time that you've spent with us with trying to sort of debunk a few myths or probably misunderstandings about trigger systems. So mate, I really appreciate you coming in, bringing some of the nuts and bolts through. Hopefully we can put them on one of our RBs and have a little bit of a play and sort of see how it all works here.
Looking forward to it.
Guys, thanks so much for watching this episode. I know it's probably a little bit tech heavy, and on that, I know that there's going to be lots of questions and sort of lots of curiosity about this topic. So please leave any questions, any comments on the YouTube video. We'll do our best to answer them with diagrams, with explanations, with a bit of text, or just give us a call at the shop and we'd be more than happy to delve into more detail into these trigger systems. As always, thanks very much for watching. My name's Scott. That's Herman.
Herman.
See you next time.